Okay. Good morning, everyone. How many people joined? 25. Okay, I think we need to make the class more serious. I think we'll have some evaluation next week. Okay. So I would like all of you to revise everything properly so that maybe somewhere around next Wednesday, we will try to have a quiz or something like a class test. Okay, so last time we talked about this molecular docking stuff. We're trying to understand how to estimate the required stuff so that we can find out the best possible compound. Can anybody tell me what is the exact difference in between the two methods? Can you broadly distinguish between the two methods, QSR and molecular docking?
Like in QSR, we are only dealing with the structure itself, like
Okay.
a dead molecule. But in molecular biology, we are giving soul to the molecule and we are seeing the live interactions with the living molecule.
Fine, very good. So in one thing we just had something, just a structure, and in another thing I said along with the structure you need to have some kind of interactions also. So that's what we are. It is one of the main differences. Okay. Like then any other difference?
In QSAR, we only consider the ligand, and in molecular docking, we consider both the ligand and the receptor.
All the time I see only 3-4 students answer, other don't. I would like them also to communicate. Any other answer? What is the difference in the QSR and docking? Can someone talk in terms of any criteria that we use in both the methods when you are screening the compounds?
In QSAR, we use activity, and in molecular docking, we use binding energy or like affinity.
Okay, that should be one of the major differences. So we are docking some kind of delta G value or binding affinity we are going to calculate. So directly you can have some software, you can feed your structure, you can feed the structure of your receptor. Now you know how to get the structure of the protein molecule. You can go to the protein data bank. If you know for a particular disease that this particular enzyme or protein is required, so you can download that, you can feed to the software. And then you can have the database of several compounds, like you have learned about the smile strings. So you can have a database which will consist of like thousands or millions of compounds of these particular, like you can consider potential drug molecules, and then you can ask the software, so it will give you the value of this binding affinity. So, but will that be a good thing? Like if you get the delta G value, if you feed to the software, will that be a good thing? Whatever values you are getting, can you trust those values? Yes. Can you trust those values directly? Like if you input the, if you give the software that compound structure and you give them the structure of all the different ligands and you get some delta G values, right? Ultimately, based on that, you can say, okay, which is the best compound or something. Which one will be the best compound based on whatever you have learned so far?
Delta G should be more negative, sir.
Delta G should be more negative. Means something it should be related with the strength of the interaction. So more the value of delta G means that compound might is going to bind with a higher affinity. Okay, so I said like the software will give you some value. So if you are using some software like a black box, that inside that you don't know what is happening, so you will just get the values and then you don't know whether those values are correct or not. Maybe then later on you will try with this your same compound some experimental studies, then you will find out maybe that compound is not at all active as your software is telling. That's why we are talking about all these different concepts. Last time I talked about different things, especially I talked about the docking, exactly what we mean by that. So docking, we defined it like you wanted to determine the interaction of two molecules and you want to find out the base orientation of ligand that will form a complex with minimum energy of complex. So we are talking about these different theories. You can consider lock and key theory, induced fit theory, and conformational ensemble theory. Now, suppose I said you don't know anything about what is going on inside the software, and you say like, okay, I am taking a particular structure of a receptor, and I'm identifying some compound which is exactly complementary to the size of the receptor. Will this compound can be the best possible compound which is fitting perfectly within the within this receptor molecule? If I have a receptor and it is having some cavity which is complementary to the size of the ligand, so it is like perfectly it is going to fit within the receptor. Will this be the best possible compound I can have? Okay, somebody has written not necessary, right? Why not necessary?
So like we can add some more fragments to this molecule to make it much more better.
uh, Fragments you can add, but my question is like this is like a perfect structure that is fitting. That's what you want. Even if you say if this is your lock and this is your
So but
key.
interactions maybe repel each other.
So this is what is important. This is what we learned. The purpose why we are talking about this theory, lock and key, that two things should be having the matching conformations, and as they should be having the complementary shape here, but along with that they should be having the chemical complementarity also. If both of the things are not matching, then if you don't know this theory and if you are simply looking for shape, so your drug molecule will fail. So that's why you need to consider both the parameters. They should be having shape complementarity and chemical complementarity. Now the another question, suppose if I take the this receptor and if I have some ligand molecule which is of this particular shape, and this is not of complementary shape to this particular structure. So can I say that this is not going to bind to the particular receptor as the shape is not complementary?
It can still bind, and maybe there'll be some conformational changes in the structure of
Huh.
either the receptor or the ligand.
Very good. So this is the purpose of your second theory, that initially you might feel that the two things are not having any complementarity in the shape, but this is the usefulness of this theory, that can be the induced fit. So the two structure can mutually adapt to each other, means the structure of the receptor can also change and the structure of the ligand can also change, and they can fit with each other in such a way that even though their initial structure were not, by looking you can say that they might not be having the good fit, but it has been found with significant research with time that both of them mutually adapt to each other. Okay, both of them until an optimal fit is achieved. So this you can consider that the use of this second theory. This should be understood, otherwise you will always look for the compounds which are always having the complementary shape or something, but that will not be the case. Okay, so I hope you understood what is this theory means. Then how to actually apply these things into when you are talking about the software. Whenever you will encounter any software, if it is a sophisticated software, on actually this kind of docking also you can do simply on the some even online you can do so on some web pages also directly feed the structure of the both receptor and ligand, and it will give you some delta G. But I said you might not be understanding what is exactly going on there. So if you go to some more sophisticated software, even I would suggest like some of you will be choosing docking as one of your mini project, and 2 3 different packages you can have. There are so many packages so you can use, and in some of the packages different options will be there. So there will be some options like when you are talking about this protein and ligand, you need to consider into some molecular flexibility, and there in the software you will be having different options like rigid body docking, rigid receptor, flexible ligand docking, and flexible receptor, flexible ligand docking. So what are all these things? Like uh, you can consider when you are considering the rigid body docking, it is going to ignore the flexibility of the molecules and they will treat them like a rigid object. If you are considering this, only the ligand will be flexible, receptor will be rigid, and in this case, both of them will be flexible. So, when you are talking about this concept, it's saying like this is one of the major challenge for your software, for your calculation. This is going to be the major challenge as how you are going to take into consideration the flexibility. If you consider there can be different cases, all these different cases, like you have a protein molecule, you have your ligand molecule. So both of them can be rigid, one of them can be rigid and another can be flexible, or both of them can be flexible. So when you are taking into consideration the molecular flexibility, what should be what should be chosen in reality?
Both should be flexible, sir.
Both should be flexible. Okay. Uh, it's saying like both protein and ligand should be flexible. So this option. Why?
Because when they are going to interact, there may be some conformational changes, no, sir.
Oh, that's what we have talked. As per the induced fit theory, there can be conformational changes. But if you see in reality, when we do the calculations, we do not actually use this one. Can anybody guess the reason why we are not choosing this one?
The target may be rigid in the
Target
real
may
life.
be. Yes, well,
Target may be rigid in the real
target
life.
may be flexible. Okay, I hope I heard you correctly. Target may be flexible, you are saying. But I can say this is also a wrong thing. We don't do this also.
Uh, so if any of the one is flexible, I think it can, like molecular docking, it can take place. Like they can bind if at least any one of them is flexible.
Any one of them is flexible. That is also somewhat an incorrect answer, but what you initially said, like both of them should be flexible, this is actually the correct answer, but we don't do that. Okay. In reality, what we do most of the time, the protein will be rigid and the ligand will be flexible in most cases. But you can say you compromise somewhere at the level of the accuracy, because what is the most perfect option? Like both of them should be flexible. Then why do we consider this? Why do we consider this in our calculation?
So maybe it will be too difficult or too lengthy a process to calculate all the possible conformations of the protein molecule because it is a large molecule.
Very good. So you can consider that protein molecule. If you see the structure, like I don't, I think till now you haven't opened any PDB file, but once I had shown you that HIV1 protease molecule PDF file, but if you open that, you will come to know how many atoms will be there So the smallest smallest kind of protein, if you consider as per our definition, we said if there are minimum 50 amino acids, so that should be the criteria. You will call that polypeptide chain as some protein molecule. So that is the smallest, like insulin is one of the smallest thing which is having around close to 50 amino acid. Okay, but if you take all the big all the other protein molecules, many of them are very, very big. Like just I'm seeing 50 amino acids. Each amino acid will be having some 10 to 15 atoms within it. So you can consider like each chain how big that will be. And if some proteins are made up of some 200, 300 or 500 amino acids, then you can consider how complex that structure can be. Okay. So, uh, like the answer should be of course this what many of you had earlier said, but this we don't take, we always take into account, we consider the ligand to be flexible and the protein to be rigid. Now this is the limitation as per our current scenario of computing power. Actually, I said, what is our job? We want to screen many compounds. Okay, in this particular subject, we want to simultaneously screen many compounds. Now, in the QSAR also, if you see, we can choose as many number of molecular descriptors, and we can try to make our model as perfect as possible by using even the multiple polynomial degrees, higher order polynomials, and we can make, but the complexity of equations, it will be increasing and it is going to take a lot many years. So then if you're talking about that you want to have some initial guesses and compared to experiment, you are trying to show that using chemical informatics I will finish my job earlier by screening a lot many compounds in the initial stages. So that won't happen as per the current. After 10 years or 20 years, maybe the more and more accuracy will be increasing as more and more factors will come into picture. So after a few years, you can consider, even though you want to screen millions of compounds, so all these, both the flexibility will be people will take into account, but not as or as they did, because if you try to do it for even maybe 10,000 compounds, so it is going to take a significant time for you if you are going to take into consideration all this flexibility. Now, why this is so much problematic, even though, okay, there are just 200, if I say amino acids are there, and even though each of them is having around, consider 10 atoms or 20 atoms, so let's take 10 atoms. So around 2000 atoms are there in each amino acid, like of course certain protein molecules I said, it can be very big. So why it is actually a problem, like finding out the just interaction of 20,000 atoms with each other. When you are going to talk about this docking, 20,000 atom of proteins are coming into picture. Why it is that difficult? In the number wise, it looks not that big that you cannot get the interactions. Here actually the main problem is, suppose if you consider this is your atom number 1, atom number 2 and atom number 3. So you can consider the atom number 1 has to interact with atom number 2 and atom number 1 has to also interact with atom number 3. Okay. So that you are, I said here you are actually putting the soul into the molecule and you are trying to identify the exact interaction. So everything needs to interact with everything. Similarly, there will be atom number 4 if that this has to interact. But then the atom number 2 also has to interact with atom number 3, 4 and as already 1. Similarly, you have to see how many permutation combinations will be happening if there are 20,000 atoms are coming into picture, how many times each and everything has to interact with each other. And these are like docking is also like it is not a very, very sophisticated calculation. There are even more advanced method where actually if you want to see in reality what kind of interactions are going on, so along with this type of interaction of each thing at you are doing at only one time step, like at a one particular configuration. But even more complex calculations can be there where they actually see the time evolution also. But this is we are not going to consider here because it is even going to become more complex. So molecular docking also you can consider some kind of approximate method where we are looking at only the configurational changes for a particular uh, aspect, like where they are arranged in a particular manner, and we are going to have some kind of rigidity, because if you try to encounter all these interactions, your calculations won't be finishing in a reasonable amount of time. If you want to have the more accuracy, then you want to make it flexible. If you are making it flexible, so this number what you are able to estimate using docking, that will be reduced down to a very small number. So you can see here, as I said, as per this arrow, the complexity is going to increase. Now, this is what I explained to you. As per the limitation of computational resources, docking has been performed with a flexible ligand and a rigid receptor for a long time. Like from whatever time the docking has came into existence, like this is what people are mostly using, and this remains the most popular method. But with time, with as the more and more computational facilities coming, uh, so people are trying to make even the receptor flexible, because if you want to increase the accuracy, somewhere with time, I said it will happen that one day perfectly the receptor can be also made totally flexible, and it will give you the most accurate value of what you are calculating. Okay, but still it is the major challenge. Now, when people actually try to give some flexibility to the receptor, and I said the receptor is a very big molecule, so they cannot make each and every molecule flexible. So there are then some other approximation. Now you have to move towards more accuracy, but you do not want to consider everything to be rigid. So what you will do, the part of the receptor which might be interacting a lot with the ligand structure, only this particular part you can make it to be flexible, and the other part can remain rigid, which is not going to interact with the ligand a lot. So this is also one, this can be one approach, that instead of making it totally rigid or having it completely flexible, you are going to have some limited flexibility. Okay, so this limited flexibility will increase a little bit accuracy at the level of the delta G value. You can see there are, if you go into the details, if you are interested in some computational stuff, you can read about this something called as protein folding problem. This folding problem, it is actually studied a lot by like very big universities like MIT, Stanford, and they try to, if you have sometimes go visit, and there is a group of Dr. Vijay Pandey of Stanford University, if you are interested in these kind of things. So you can understand just amino acid chain which you have in your body, and acid ultimately the folding happens and it gets converted to a three-dimensional structure on which the function of a particular protein is dependent on. Even if you just want to understand how the a particular structure is going to fold into what particular structure, this is very difficult to identify using the computers, because the calculation what it takes, this is on the order of some seconds. Okay, and just even simulating the thing, just to do the calculation of a single protein chain at the level of this thing is a very difficult task. So these particular groups at Stanford, they actually deal a lot with machine learning and development of some new packages, where they try to get the computational resources throughout the US, or I think even maybe they might have crossed the boundaries of the countries also. And wherever people can contribute their own computational power, they ask them to download some software so that they can use their computing power and they can do this calculation, even to identify the interactions at the level of just times level of seconds. So you can just consider how difficult this is at this particular time to understand at a very, like if you are saying what is going to happen after 5 minutes or 1 hour, this is very difficult task. So at this molecular docking level, we are just trying to identify, you have a receptor, you have some ligand, how they are going to interact, but you are going to have the assumptions. Okay, so two models, you know. Now, suppose in the these two theories are done. Then there is a third theory that has been developed just, you can consider compared to these theories, it has been developed just recently. It is called as conformational ensemble model. So what is the meaning of that? So what is conformation?
Changing in the structure a little.
Okay. So structure, conformation means structure, and ensemble means collection.
A group of.
Yeah. So there can be so many structures for the same protein. Now you know so many times this COVID problem is there, so people will say whether the same vaccine is going to be important. I think somebody even asked this question initially. So if there are mutations within the structure, so then there is no guarantee. Maybe if the genetic sequence or something is not changing much, so maybe the same vaccines are useful. And most of the time, these water mutations happen, as I know, they are not happening much at a time. So the same vaccine might be even it's good even for the long time. So same thing you can consider for your protein structure. So in proteins, they are going to have continuous changes. Like they are not going to remain this in the same form all the time, even though the final three-dimensional native structure, whatever we are saying, but they will be also having some slight changes happening uh, throughout the time. Like it won't be a perfect structure all the time. So these three-dimensional structure will be always, if you are considering it is changing, even though it is not changing much, but even though it is changing slightly, this is going to have the effect. If there are two multiple conformations, so the two different conformation with the same ligand, it will be interacting differently. So different values of delta G will be having in both the cases. So it is not always the case that you have to always consider the one particular structure, but multiple structure also should be considered. So this is what this conformational ensemble says, that whatever structure you are assuming, this is not always in the same state, but they are always, they might be changing. So you should consider the possibility of all the structures. So this is somewhat actually related with the earlier theory itself, that there can be induction in the structure even after fitting, but even without something else coming closer to this, without that also the structure can be flexible and it can adapt different conformations. So this is what the third theory says, that when you are considering docking, actually not just the one particular shape, but if you see here, there are multiple structures have been considered, 1, 2, 3, 4, 5 up to n you can consider, and all of them have different forms. So some of them might be in some inactive form, some might be in active form themselves. Sometimes upon binding of different things, they can change their conformation. About binding of certain things, they might not even change anything. So this plasticity or their flexibility you have to always consider when you are doing docking. Okay, here I have written clearly, if you are having like protein conformation can change itself in many forms and not just upon binding as indicated by the your previous model of induced fit. So if you now see all these three theories, this you have to consider the first theory, the lock and key model. It talks about that there is a shape is coming into picture. So somewhere that rigidity it was considered, but I said along with the shape, you have to also consider the chemical complementarity. So the first model is talking about the three-dimensional complementarity, like the shape and chemicals nature. The second theory, it talks about how the complementarity between the two things is going to be achieved, and the third thing is going to talk about the how the different structures can be there. So you have to take into consideration their conformation complexity. So they say even like all these three things are just related to each other; they are not contradictory, and each one of them is going to focus on the particular process of. Each one of them is going to focus on some aspect of your recognition process. Now the next thing is what you're going to do in the exact docking. So when you're going to do docking, you have to estimate the binding affinity, but along with that, you have to, your software should be able to estimate something called as pose. What is this pose? Uh, so I said there are two things, pose and binding affinity. So pose means three things. Prediction of ligand conformation as well as its position and orientation. Now, what is the meaning of all these different things? Like you want to predict the ligand conformation. So I said in many of the thing, you are going to keep the ligand flexible. Why you are keeping ligand flexible? Can anyone say like why we are keeping the protein rigid, but we are keeping the ligand as flexible? Why?
So like ligand
The
is a
ligand
small
molecule is
molecule and it's
small.
easy to find out its
Yeah.
changes.
Yeah, so ligand always we have said it's a pharmaceutical compound needs to have small molecular weight. They will be having very less number of atoms, so their flexibility we can afford to calculate. So you have to keep the ligand flexible. So ligands different conformations might come into picture that you have to consider. This is the first thing. Then second thing you have to consider the position and then orientation. What is the meaning of position here? Like if the receptor is there, in the earlier I had shown you this particular image. So here positions are clear that at different position this can bind and different affinities can come into picture. Right. So all these different positions also you need to screen when you are actually doing docking, not just one particular state. Okay. So different positions of binding. And the third thing is about orientation. So orientation I mentioned to you that day, if you are having the receptor and if you are having this particular, suppose this can be a good way to show. So it can bind like this and the functional group can stay outside, or it can bind like this functional group can be inside and this can be other end. So the relative orientation is also important in what way it is binding, and people actually try to tune this experimentally, once you know that which particular orientation are good for the binding. So when you're talking about these two things, identification of poses, like all the different poses along with the orientation and conformation can come into picture that you can see in this particular images. Like this can be pose 1, this can be pose 2. So in pose 1, there is for your particular same drug, there is a conformation A1. For the same drug, there is a conformation A2. Similarly, for your protein also, if you are making it flexible, it can be having different conformation. Okay, similarly with the orientation also it can bind at a different places. So each of these you can consider the pose or that is the binding mode. So when you're talking about this, these two steps, identification of pose and binding affinity, these are called as something called as search algorithm. The way you are calculating the poses, it is called as search algorithm. And the way you are calculating the binding affinity, it is called as scoring functions. So now each and every method, some kind of mathematical functions will come into picture. In the QSAR, you directly had the QSAR regression models. Those were your mathematical functions. Here you are having some scoring functions which will be able to calculate the binding affinity for you. So if you see these poses, like search, the first thing is search algorithm, which is going to identify the poses. This we are not going to deal much. This is a lot intensive computational stuff. Maybe if next year I take some a new course, there will be, we'll see these are some complicated simulation things like Monte Carlo simulations, molecular dynamics simulations. All these different things comes into picture, which has, like, you can consider like what the software will do in this for each thing. Different conformation it has to continuously generate. Okay, so this will be generated as per the instruction within the algorithm, and you can see then the same ligand which is you are having, at which particular position it has to you have to keep, and accordingly find out, like suppose this is the step 1, so delta G of step 1 will be what, if it is binding at this particular place, so how it will be. So this how this kind of change in the position of the particular thing happens. So accordingly, different poses will be generated, and for each poses delta G will be varied. So how to come up with these different poses computationally? This is right now not the our task. I will just explain in short how to do that. But what most important thing here is your like this is also important. But I said we won't be dealing with this. This more sophisticated. We are going to deal with this scoring function. This you should understand in more detail so that to understand what is the criteria that binding affinity. How do you exactly estimate? So scoring function is I said is the delta G value, and this is what you are going to use for assigning the priority order. Now, when we are talking about this scoring function, this is related to your calculation of delta G binding. This delta G binding, again, you can consider what it is: energy required to separate your complex into its separate part. That I showed you the definition. By this, you can mean delta G of binding is equal to energy of the complex minus energy of protein minus the energy of ligand, or I said you can say from the complex just addition of the individual energy. If you do, you get the delta G binding. So even though this equation, this is what your scoring function is actually. What I said, no, that you need to calculate the binding affinity here. For the binding affinity, the scoring functions are needed. So this is the equation for that which you should use while calculating. You should calculate in your software what is the energy of complex, what is the all these different energy, and you should come up with the value. But this is just a very generalized way of representing the formula for calculation of delta G binding. Now, in reality, I said if you know thermodynamically we said uh, like the delta G value should be negative. Now, this is what we are going to get. But do you have any other idea like delta G value on which other factors it is dependent on thermodynamically? Know any formulas for delta G?
Equilibrium constant.
Sorry,
Equilibrium constant.
equilibrium constant. Yeah, that is one of the aspect. Any other formula do you know for delta G thermodynamically?
Or like a delta H minus T delta S.
Yes. So there is another thing called as delta. Like it will be dependent on equilibrium constant that we are not seeing here, but that can be also delta G is equal to minus RT ln K. But what we are going to deal here, as we are going to see into details at the molecular level, delta H minus T delta S. Now, when we are talking about just the energy of complex minus energy of the individual thing, actually you are talking something about when you are talking only about energy. So actually you can say uh, this is given in a very crude way. When you are talking about the delta G, the interaction, they need to understand in terms of some bonding, like what kind of bonding I mentioned to you. When some suppose chemical reaction happens in your laboratory, uh, how do you identify whether what kind of bond formation or bond breaking has happened? How do you estimate that in the laboratory? If the two things are binding with each other, or if suppose there is a reactant A, reactant B is there, and it is changing to C, so some kind of bond breaking and bond formation is happening. So using which thermodynamic parameter do you estimate this? Okay, somebody has written temperature. Sometimes you talk about all this endothermic and exothermic reaction. You basically talk about the delta H value, okay, enthalpy of the reaction, right? So based on this, what kind of idea do you get? Like delta H value, you try to identify, it means if you are knowing some number related to this, you can talk about how many bonds have been broken and the new bonds have been formed within the structure based on the enthalpy chain. Similarly, in at the molecular level also, you can talk about, even though this is happening at the level of protein and ligand, but there can be some changes related to bonding. So you can talk about this delta H value. So these equations can be made even more complex. And apart from that, I don't know whether you have studied this, but delta S value also will come into picture when you are talking about the delta G value. So you might be having idea about the entropy related stuff, that this is something related with the order and disorder of the system. So there will be some changes that will be happening when both of the things are binding to each other. So how to take into consideration even all these effects when the binding is happening, how the structures are getting ordered or disordered. So that also we need to consider, so that we can make this generalized formula a more accurate. We can convert it into a more accurate formula that our software can calculate. So that's what I said. This is what the scoring function, which will be for our next discussion. We'll talk about this, our fast approximate mathematical method, how to estimate the interaction. These interactions are nothing but what Prabhu earlier said, the strength of the non-covalent interaction we are going to find out. I will talk about this later in more detail. It will be more clear. Any questions here? Okay, how many people are there? Just 41. Okay, again, I ask you guys to join. Generally, I join every time for the class even start. I request all of you, like, please be there in the at least first 2-3 minutes. If there is another class before my class, it is fine. But otherwise, please join at the earliest. Okay, and I said that next Wednesday, most probably, I'm going to take a class test or quiz. So consider just like anything I can ask. It can be a conceptual test. So just revise whatever you have so far. Whatever slides will be there in your folder, Google Drive folder. Just revise all of it. Okay. So if you don't have any questions, you can leave.